and welcome to the energy review. We're going to go through and review some of the main ideas around energy and work and power. And actually I don't think we have any questions today on power, but we did a big power practice worksheet last time that you got cleared off by me, so you should be good there. We're going to primarily focus on conservation of energy or energy dissipated and work. Before we jump into the problems, I want you to know that you can work through the review on your own and then check this with the video, or work through with me during the video, or try a question, then watch that part in the video, try the next question, try that part, watch that part in the video, whatever works for you. Before we go and start the problems, we should get all of our equations, all the ideas onto this place right here on the energy review so we don't have to keep flipping through our notes or looking up on the board. Energy. There are three types of energy. There's kinetic energy, and the equation for that is 1/2 times the mass times its velocity squared. There's also gravitational potential energy. Equation for that is mass times gravity times height. For Earth, gravity is always 10. And then last up is spring energy, and that's 1/2 times the spring constant, that's the letter K, spring constant, times the displacement of the spring. X is displacement there. So those are all of our equations for the types of energy that we know. We said that if energy is not lost or added, then all the energy was conserved. So all the energy we had initially was going to be equal to all the energy we had finally. Okay, and that's if there's no energy lost or added. If energy is lost, then we know that you're going to start with some initial energy, but you're going to end up with less final energy and some energy dissipated. That's what we call energy lost. And we add it like that because dissipated energy, you can't get that back, and you typically lose that through things like friction. Okay, so if energy is lost, you start with initial energy and you end up with some final energy which is less than your original initial energy and some energy dissipated. Last up we had when energy was added to the system. So if energy is added, whenever you're adding energy into the system, we called that work. So energy initial plus work equaled energy final. Kind of section this off here. So those were our three cases. No energy is lost or added, just energy is lost, or just energy is added. And you got to ask yourself, is there friction going on here? Does it mention energy being lost? Does it say there's a force acting on it? Is energy added? Which brings me to what we know over here about work. Work is equal to force times displacement. So if you're doing a problem and it's asking you how much energy was added or how much work do I need to find, you're either going to use force times displacement or this conservation of energy equation. And the last one that we had was about power, and power is equal to work divided by time. And that was that whole power practice we did in the last class. I don't think there are any power problems on this. So it's kind of a big review of all the equations. Get those written down, and then let's begin on our first problem. On to problem 1. We're going to start real easy. Problem 1 and 2, these should be no problem with you. We've got a ball is resting on a compressed spring. What type of energy is present in the system? So this is the first part of part 1. Kinetic is the energy of things moving. Dissipated is energy lost. Gravitational is the energy of height. And elastic or spring energy is the energy of springs. So that's going to be elastic energy there. It says this ball is resting on a spring that is compressed 0.87 meters, and it has a spring constant of 39 newtons per meter. How much energy is present? Well, we just said that it's all elastic energy or all spring energy. So we're looking for spring energy. We know that the spring constant is 39 newtons per meter, and we know that the displacement is 0.87 meters. So now I'm going to find my equation that relates all these. Spring energy is equal to 1/2 times the spring constant times that displacement squared. This is 1/2 times 39 times 0.87 squared. And if we put this all out in our calculator here, you should get about 14.8 joules. Remember, energy is always measured in joules. Next up is problem number 2. In problem number 2, we have a hockey puck that's moving swiftly across the ice. What type of energy does it have? Remember, elastic energy, we just talked about that. That's the compression or stretching of springs. Gravitational potential energy is the energy of height. Technically, if we said something below the ground was 0, maybe it could have gravitational potential energy, but typically we make the ground 0, so no gravitational potential energy for our hockey puck. Even though ice isn't perfect, we like to imagine it as a perfectly frictionless surface, so there's not going to be any dissipated energy. That hockey puck has the energy of movement, so it's going to have all kinetic energy. If that hockey puck has a mass of 0.175 kilograms and it's moving at 5.5 meters per second, what is the energy of the puck? We just said that energy that's going to be present is kinetic energy, so that's what we're looking for. And we know that the mass is 0.175 kilograms, and we know this velocity here is 5.5 meters per second. I like to write all those out so I know what I know and I know what I'm looking for, and I can figure out how to tie those together. Earlier we wrote that kinetic energy is 1/2 mass times velocity squared. So we're going to plug in those variables. 0.175 is the mass and the velocity was 5.5. Square that. And if you calculate this out, this is 2.64 joules. Energy's in joules. This right here, figuring out what variables you know, what you're looking for, the equation that relates those, and plugging in those correct variables for the correct numbers for the correct variables, that's the physics. If you're struggling to calculate this out or need help with a calculator, let us know and we can do that. But the figuring out what you know and what you don't know, what equation relates those, and plugging in those numbers for the right variables, that's the physics part, and this is the little piece of algebra we have to hold you accountable for. Alright, let's move on to the next problem. Alright, problem number 3 looks a little intimidating. There's parts A through F, but I assure you that this isn't too difficult, and you guys know what you're doing here. We have a bungee jumper that's jumping off a bridge. At the moment that he leaves the bridge, what type of energy does he have? So there's the bridge, he's standing away up there, high above the ground, and he's about to jump off. He's not moving yet, so what type of energy is he going to have? Well, he's going to have the energy of height, and that's gravitational potential energy. That's what he has there at the top of the bridge. Next question says that if that bungee jumper has a mass of 102 kilograms, and the bridge is 99.2 meters tall, how much energy does he have? Well, we said at the top that he's going to have gravitational potential energy. So we want to figure out how much of that does he have. We know his mass is 102 kilograms, and we know the height is 99.2 meters. Our equation for gravitational potential energy is mass times gravity times height. We just said the mass was 102. Gravity not given to us, but it's one of those things you should definitely know by now. That's 10, and the height is 99.2. A lot of big numbers we're multiplying here, so we're going to get a big number out of this. And you're welcome to round a little bit if you'd like. I get 101,184 joules of energy. That's a lot of energy he's got. All gravitational potential energy at the start, but that's all the energy he has there. Okay, all gravitational potential energy. Part C says when this bungee jumper is halfway down, the bungee cord is about to tighten. So it hasn't tightened yet, meaning it doesn't have any elastic potential energy or spring potential energy in it. But he's already halfway down from where he was falling. At the top he had all gravitational potential energy. As he's falling down, before the springiness takes part, and he's halfway down, he has half of that amount of gravitational potential energy, and then he's also going to have kinetic energy. And it says, how much energy does he have when he's halfway down? Well, up above here, it says assume that there's no energy lost, so no energy dissipated. If he's not losing any energy and he's not gaining any energy, he's still going to have this same amount. Okay, there's no energy lost, no energy added, so he's still going to have, since initial energy is going to equal the final energy, we didn't lose any energy, didn't gain any, he's still going to have 101,184 joules. Didn't lose any, didn't gain any. Next up says when the bungee jumper is halfway down, how fast is he going? We want to know what is his velocity when he's halfway down. Well, we know that initial energy still equals final energy. So we're talking initial at the very top, final is halfway down. Initially, he still has that 101,184, and when he's halfway down, he's still going to have that as well, but he's going to have some gravitational potential energy there and kinetic energy, 1/2 mv squared. So this is 101,184. His mass is 102. Gravity is 10. We're halfway down now, so the height's not going to be 99.2. The height's going to be 49.6. I just did 99.2 divided by 2 there. So that's 49.6 plus 1/2 times his mass again of 102 times v squared. And we're solving for v. Pesky v that's squared. We're going to have to take a square root later. I'm going to section this off because we're going to keep working over here. You guys are getting intimidated now because we've got these numbers. There's this conservation of energy thing. We have numbers and there's all these things. Let's simplify it. 101,184 equals this right here, I'll multiply it out, is 50,592. 1/2 of 102 is going to be 51 v squared. And then I can subtract this portion over, divide by 51, and then take the square root and get v. So I'm subtracting this over, dividing by 51, and then taking the square root. You end up with that the velocity is going to be 31.5 meters per second when he's halfway down. Okay. Last up it says, not last up, the bungee cord catches the jumper and goes completely tight, and it stops him just as the jumper's hair is brushing the ground. So he's barely reached the bottom of the ground, the bottom of his fall. How much energy does he have there? We didn't lose any energy. We didn't gain any energy. So the total amount of energy is always going to stay the same in this problem. So he's still going to have 101,184 joules. Energy stays the same. We didn't lose any. We didn't gain any. If the bungee cord is stretched 42 meters, what is the spring constant of that cord? Remember, initial energy equals final energy. The initial energy here was 101,184. The final energy that we end up with, we're at the ground, so we no longer have gravitational. It's a bungee cord, so it slowly comes down at the very bottom. He's at rest, so there's no kinetic. It's going to be all spring energy, which is 1/2 kx squared. Now we can substitute in these values. We're looking for k, and we know that x is 42 meters. So I'm going to put that in parentheses, square that. This becomes 101,184 equals 882k. I just squared the 42 and multiplied it by 1/2, and you end up with k equaling 115 newtons per meter. Remember, through this whole problem, energy was conserved. It said you don't lose any energy, no energy dissipated. We weren't doing any work, we weren't adding energy. So the energy always stays the same. I think the hardest part was that, recognizing energy stayed the same, and then recognizing at each point in this fall for the bungee jumper, what types of energy did he have. Hopefully going through that helps you figure that out. Problem number 4, we have a 2,141 kilogram roller coaster cart that starts out with 0 velocity, so it's starting from rest at the top of a 254 meter hill. How much energy does the cart start with? Well, first we need to identify what types of energy it has. Starts from rest, so that means there's no kinetic energy. Hasn't done anything yet, so there can't be any energy dissipated. There's no spring or elastic energy because it doesn't mention anything about a spring being stretched or compressed. And it does say that it's up on top of a hill, so that's going to tell me that we have gravitational potential energy here. Gravitational potential energy, and the equation for that is mass times gravity times height. Big roller coaster, 2,141 kilograms, gravity's 10, and it's way up there, 254 meters up in the air. Multiply all that out, and we have a giant number on our hands. 5,438,140 joules. Remember, energy is always in joules. That's how much energy this guy starts out with. Do we need to keep this number so precise? You could round it down if you really wanted to, and I'd be okay with that. I'm going to leave it as is. Later on, part B, it says the cart is moving at 21 meters per second at the end of the ride. How much energy does it have now? Well, it didn't tell us that no energy was lost, so we can't make that assumption. So let's just solve for how much energy it has, and then we'll compare them later. It says it only talks about it moving at 21 meters per second, and the energy of movement is kinetic energy, and that's 1/2 times the mass times the velocity squared. Remember that mass, 2,141. The velocity is 21, and that has to be squared here. Much smaller number. I mean, it's still big, but smaller compared to the previous one, 472,091 joules. So what happened here? We started out with a ton of gravitational potential energy, almost 5.5 million, and then we ended up with only about 500,000 joules of energy at the end. Why is there a difference in this energy from beginning to end? I mean, maybe the engineers built it that way, but that's not a good explanation. People screamed, okay, that doesn't make sense. Never mentioned anything about a spring. Whenever we lose energy, it's because energy is dissipated. Could you calculate how much energy was lost? Well, that's part D. How much energy is lost? If energy is dissipated, we know that energy is lost. Initial energy is going to be equal to final energy plus energy dissipated. Remember, our initial energy was that huge number, 5,438,140. Our final energy was 472,091, and we're solving for energy dissipated. So if we subtract this from both sides, you get the energy lost from friction, or that energy dissipated, is 4,966,049 joules. That's how much energy was lost. A lot of friction on those roller coasters. We're on our final problem for the energy review. This is problem number 5. We have 3 students that are arguing who is the most powerful. There are 32 stairs, and each stair is 0.11 meters tall. That's 11 centimeters. Each student starts from rest and ends at rest at the top of the staircase. Below we have the student's mass and the student's time. I lied. We're actually going to do a problem today with power, and that's this last part here. But first I want to calculate the work done by each student. Who did the most work? There are 2 ways to find work. One of them is force times distance. It doesn't mention anything about force. The other one is conservation of energy. If we're adding energy to the system, we've got our initial energy plus the work, the energy that we're adding, that's going to equal the final energy. We start out with 0 energy. We end up with all gravitational potential energy. So the work here is going to be equal to mass times gravity times height. And we're going to use this to figure out how much work Davy Crockett, Peter Pan, and Elvis Presley did. If you can tell me what song that's from, might give you an extra bonus point on your test. Calculate the work done by each student. So let's do Davy Crockett here. His work is going to be equal to his mass times his gravity times his height. So his mass is 82.4. Gravity's 10. Uh-oh. What is this height? It's the height of the stairs. Each stair is 11.11 meters tall, and there's 32 of them. So 32 stairs times 0.11 meters is 3.52 meters. That's our height there. Okay, so we're going to have to use that. Height is 3.52 meters. This ends up being 2,901 joules. Section that off. Now we'll do Peter Pan. Again, mass times gravity times height. So his mass is 92, gravity's 10, the height's still the same, 3.52 meters. That's how high in the air he goes. Peter Pan does 3,238 joules of work. And last up is Elvis Presley. His mass is 74.1 kilograms, gravity's 10, height is 3.52, and the work that he does is 2,608 joules. So which of these students did the most work? Peter Pan did the most work with 3,238 joules. Now I want to compare and I want to calculate the power used by each student. Which of them is the most powerful? Our equation for power is work over time. Okay, power is work over time. So let's do Davy Crockett here. His power is going to be work over time. Well, his work was 2,901, and Davy Crockett's time here was 4.07 seconds. And we get an answer of 713. Do you remember the unit for power? Think about that. Power is measured in watts, which I know is confusing because it looks like a W, which is what we use for work, but it's powered in, the units for power are watts. Let's check out Peter Pan. Peter Pan, the power here is going to be his work divided by time. Peter Pan's work was 3,238 joules. Peter Pan's time is 4.12 seconds. 4.12. And the amount of power that Peter Pan used was 786 watts. Last up is Elvis Presley. Power's work over time. Elvis Presley, 2,608 joules of work. His time was 3.98 seconds. And this ends up being 655 watts. So which of our students was the most powerful? It's Peter Pan with 786 watts. Is it necessarily the case that the person who does the most work is the most powerful? No, that's not always the case. Think about it. If Davy Crockett had a time of just 2 seconds, 2,901 divided by 2 would have been something like 1,450 watts, so he'd have been the most powerful. So it has to do with work over time. This problem I know for sure is definitely going to be on your test. Same type of idea, comparing 3 students, figuring this out. Make sure you can work through this problem, and that really goes for all of these problems, all of 1 through 5. That concludes our energy review. Did some good problems with conservation of energy, energy dissipated, work, power. All comes back to this, okay? You don't have to memorize these. They'll be given to you, but you really need to know what they mean. If you have any questions, let me know, and good luck studying.